Good morning and welcome to Physics 4C. Today is April 7th. Today is actually the last day before spring break, where we're going to be meeting in here for this class. We will have our exam on the week after spring break. So after the spring break, we're going to resume the class basically after we do our midterm. Our midterm, as I mentioned before, covers chapters 12, and then 15, 16, 17, 18, 19, and 20. So all of these chapters are covered in this exam. The focus might very well be on chapters 19 and 20. 19 and 20 are actually one chapter together, and where you calculate the work, you calculate the heat, you calculate also the efficiency, you calculate all kinds of processes. You guys saw also in the lab there are a bunch of engines that basically you did a lot of calculations for them. So this is typical, okay? At this point, there is also another emphasis on waves when it comes, especially to wave interference, especially when it's related to the Doppler effect, to the beats, and these concepts related to waves. So that is really, if I were preparing with you guys in the exam, this is the focus that I need to do for this entire section. There will be 4 problems in the exam. 4 problems will be basically, there will be a question and a lot of space underneath to answer that question, the problem, and then there will be a lot of space to answer the questions. Usually each problem is made up of several parts in it, either 2, 3, potentially 4 or 5. Especially when it comes to engines, you might have a lot of questions. And this is one example that we're going to do today for an in-depth, basically, analysis of a cycle describing an engine. This is actually a practical engine today. So you're going to be meticulous, methodic in your calculations, starting from the point that you have the information, and you follow through basically to answer all of the questions related to the problem. Then you will have the back also of that paper where you can actually also continue the answer if you need to. In addition to that, you will be provided by, so there will be at least 4 pages, basically each page covering one problem. And then you will have a formula sheet that includes all the formulas you will need for this exam, okay? So you don't need to bring anything from home other than 2 things, really, a pencil and also a calculator. You need a calculator, especially for this class that is scientific, that can do the natural log for you, okay? You can actually do calculations because, as you can see, we have trig functions, we have logs, we have all kinds of things, exponentials, and also raising to the power of. And usually it's not like a square root or anything like that. When you raise something to the power gamma, and gamma happened to be 1.67, you do the math. Or gamma happened to be 1.33 or 1.4, you have to do the math. Or gamma minus 1. So this is typical stuff that you have in this part of the class. Then after that, we still have 4 more chapters, chapters 33 and 34. 33 and 34 deal with optics, geometrical optics, okay? And they deal actually with 2 basic laws in that section, and they are Snell's laws, the law of reflection and the law of refraction. And then, but we have a lot of applications for that, for optical devices, basically mirrors, flat mirrors, convex mirrors, concave mirrors, and also lenses. Lenses also come with a different variety of lenses. You have converging lenses, diverging lenses, lenses where they're actually on one side converging and diverging on the other side, or flat on the other side. So there's all kinds of geometries involved with optics. So we're going to get that through chapters 33 and 34. And then we get into wave optics and phenomenon related to interference, basically, especially in the double slit experiment where you have a monochromatic light goes through 2 small holes. That is where the wave nature of light comes into play. It's no more geometrical, and you'll have interference in here. And basically, dark fringes and bright fringes form on the other side on a plate that is collecting them. We're also going to explore the single slit experiment, basically, where you have a monochromatic beam goes through an opening that is small. And again, you're going to also see interference phenomena on the other side related to the wave nature of light. So that is chapters 35 and 36, and that will be the end of this basically class. So we still have 4 more chapters, and the 4 more chapters deal with optics, whether geometrical optics or wave optics. Harris, if you have a moment after class, we probably have to meet. Of course, it's not going to be recorded, so we can talk a little bit, if you don't mind, okay? Or we can meet later if you don't have time. We can meet some other time at your own convenience. Good? Okay, no problem. Good. Anyway, so the problems I thought we should do, and let me first of all pull my notes in here. And this is physics 4C. And we're dealing now with, okay, let me open a new section in here and call it CH20 problems. And let me share with you that screen. Share the screen. Okay. Okay, so the first problem that I thought we should do is problem 47. This is actually summarizes the entire chapter, this problem. So it's a very important problem that we have to go through in detail. The other problem that I thought we should do is another problem that is a little bit different, but actually covers the same stuff. It's problem 42. But as another important problem that we must cover no matter what is problem 52. So this is a must. This is a must. The other problem that I think is important also is problem 53. And the problem that is kind of long also and requires a lot of time to finish, but it's actually similar to problem 47, involves a different kind of engine. So this will involve the engine that we did in class, and this is the auto engine. This is for regular cars. The other engine that we're going to be talking about is 56, and that is the Stirling engine. And I have several of those engines in my home. Actually, I've shown you probably a couple already. So that is the Stirling engine. That depending, okay, so if we have time to get into it, it's fine. If not, the processes are different. So the math is different, but the idea is the same, okay? And that is actually similar in a sense to also problem 42, which is also completely different and practical engine, but also the ideas are the same. The math is different. And that is also true for 34. But 34, I'm not going to do it now, but I'm thinking that you guys need to look at it. The reason why 34 is worth looking at it is actually one of the 8 engines that we have in the lab. Last time when we had the lab session, a lot of you guys left, but one of you guys hang around with me toward basically the end, and we went through the entire calculation for processes like this one. So problem 34 is one of the 8 labs that one of the 8 engines in the lab that we have. So I'm not going to do it because you guys are supposed to do it in the lab. We went through it in the whole discussion. If you think you need help with it, please let me know, because all of the 8 engines in the lab, 8 of them, okay? They're part of your exam preparation also, all of 8 of them. Okay, and this is one of them. So if you have difficulty or if you have questions about the lab, please do not hesitate. I know it's a spring break, but if you ask me a question during that time, and if I'm out of and not near a computer, I may not reply to you immediately, but I will afterwards. I will at some point say, oh, hey, this is the thing. And if it is something that benefits the entire class, I may even record that and publish it so that everybody else gets the benefit from it. After all, labs are not exams. They're just to prepare you and help you do well in the class so that you understand the concepts. So you do all of those activities. So it's part of the learning process. That's why you're encouraged to do those problems together, to do the labs together, and to do the homework together, because it's part of your learning process. So it's not like an exam. You're going to lose points if you work together with somebody else. It's not cheating at all. As a matter of fact, it's encouraged. Okay, so these are the things that I thought we should do. There is a fun problem, but I don't know if we get to it or not, honestly. It's problem 32, and that has to do with biology and metabolism and how much entropy changed in the system and so on and so forth. Okay, so let's get going with problem 47 because it's a long problem, and I'm hoping to get through it before the end and get at least to problem 52 in the process. Okay. Problem 47. So it gives you basically, it gives you the cycle that we did in class. So this is problem 47. That's what we're going to start with. So it gives you in the PV diagram a starting point. So this is the point A, and then you go on an adiabat. I know it looks kind of isothermal, but this is supposed to be an adiabat. Okay. So to point B, and you go through an isochoric process to point C, and then you go back. This end usually is a little lower, so I draw it a little bit there. To point D in this way. So you go you go clockwise, which means it's an engine. Obviously, the work is this entire thing in here. So point A. So this volume and this volume are related to one another. So this is RV and this is V. Okay, where R, or sometimes rho, actually in the lab we call it rho, is the ratio of the volume in A over the volume in B, okay, or the volume in D over the volume in C. It's the same ratio, okay, because these two volumes, VB is equal to VC as a matter of fact, and VA is equal to VD. This is the Otto cycle. This is the one that exists in cars, okay? As a matter of fact, this car is a Passat, a VW Passat, okay? Has a 6-cylinder Otto cycle. So this has 6 cylinders. That means you have 6 of this working together to do this. So this is 1 cylinder. So this is 1 cylinder doing all of this work. So if you're curious about the cylinder, this is how it looks like. I'm sorry, that's not correct. So there is the intake valves in here, or the exhaust valve, and there's the intake valve in here. And so there is a chamber in here, and there is a piston in here that can move in and out. Okay. So this is your piston. And as it's moving up and down, it's basically going to cause the whole mechanism in here to change. Basically, it's going to turn the flywheel, part of it. So it's not just this cylinder. This is not a single cylinder. This is not a motorcycle. So this is basically is going to do that reach. So when it's fully compressed, this is at this point at VB equal to VC. So this is the volume V. When it's completely relaxed, this is actually equal to RV. This is the point that is at point A and then point D. Okay, so this is the engine that we're talking about. The ratio R in this problem is given to be 10.6. So this is how they make VWs. How big this volume, this overall volume, versus this small volume is 10 times, a little over 10 times more, okay? The diameter of each cylinder is called the bore, and that is 82.5 millimeters. So it's 8.25. So this distance from here to here, the D is 82.5 millimeter. Okay, so that is the diameter because it has a cylindrical shape. And the distance that the piston moves during a compression, and the figure called the stroke, is 86.4 centimeter. So the stroke is this distance. That is S is equal to 86.4 millimeter. So it's not the entire chamber itself. It's not the entire cylinder, but how far the piston goes up and down, that's all. So basically when it's fully compressed, it's here. When it's fully relaxed, when it's fully basically expanded, when it's in this point in here, in point A or point B, it has traveled this whole distance, which is 86. So basically, you can clearly see that the difference in volume between A and B, for example, VA minus VB, is equal to clearly this volume at point A, which is pi times the diameter over 2 squared times this whole length, whatever that is, okay? And the other one is just this one. So it's just the difference between these two volumes is this number, that's all, okay? Because this volume, the entire volume VA is from the beginning to the end, okay? The volume in here itself is VB. So the difference between them is this empty volume. And that empty volume is basically the area, the base area, which is pi times the radius squared, times this height in here, which is S. So this is the difference between the volumes. Obviously, this is RV minus V. And that is equal to this difference. So from here, we can find the volume by taking V as a common factor as just 1 over R minus 1 times pi over pi times, there is no over 4 if you want to write it over 4, times D over 2 squared times S. So this is this volume. That is VA, that is VD. I mean, VA, that is, no, I'm sorry, not VA, VB and VC. Okay, so this is the volume, this one, this volume, the shaded volume. That is in this point, that is V. So we can find already V, the volume of the cylinder. Since we know this volume, we also know this volume, RV, because R is given 10.6. So this is the volume then at this point. So the volume at points A, which is the same volume at point D, is just R divided by this number, or R times this whole number, which is R over R minus 1, pi times D over 2, squared times S. So basically, we know these two volumes. That is the bottom line. Just by this information that was given to us. Since they gave us the stroke, the distance traveled, so I can find this empty volume, the difference between the two volumes. And since I know how the two volumes are related to one another, this volume is just R times this volume, and R is given. The compression ratio is given, which is R. So this is the compression ratio. And this is the stroke. So we know, we have everything that we need to know for these two volumes. And they are the only two volumes that matter in this problem. Okay. So the initial pressure of the fuel is 8.5 times 10 to the power 4 Pascal. So we know what this pressure is. So this is the pressure at point A, PA. So this PA is given to be 8.5 times 10 to the power 4 Pascal. That's given. Remember, we know the volume VA. This is this number. This whole thing, because we have D, we have S, and we have R. Okay, obviously, we have to convert D into meters, and we have to convert S into meters, and we plug in the numbers in here. R is dimensionless. R is just the ratio of the two volumes. It doesn't matter what they are. Okay, so, and it's given too. So we should be able to find this volume RV, okay, which is VA. And then also, and the initial temperature, which is TA, is room temperature, 300 Kelvin. So we know the point in here, we know its volume, it's RV, we know its pressure, and we know its temperature. So we technically can find N from this equation, PA, VA equals to nRTA. So we have everything in this equation. The only thing we don't really know is what this number of moles is. So we really need this number at some point because we probably are going to calculate these things. So N is going to be PAVA over RTA. TA is 300 Kelvin, VA is this volume, plug in the numbers, and PA is given to be this number in Pascal, which is SI units already there. Okay. Assume that 200 joule of heat is added to each cylinder in each cycle by the burning gasoline. The heat is going to be added only here in this stage, because this is an adiabat. This is Q is equal to 0. This is Q is equal to 0. Both of them, there is no heat in them. This is where the heat is added. And we're saying, what they're saying is 200 joules is added in here. They didn't tell us how much heat is being dumped in this stage in here, because that's where we close the cycle and we have to get rid of the excess heat, okay? So, and the work is the green zone. The work is the area that is composed in there. So they are telling us Q hot is equal to 200 joules. Because there is no heat through the adiabatic processes from A to B or from C to D. There is no heat in there. Okay. Okay, so and that the gas has a CV, so they gave us also CV. CV equals to 20.5 joules per mole per Kelvin. Okay, they gave us CV. Now we really don't need anything else, but they also gave us gamma. Gamma is 1.40. Remember that CV and gamma are related to one another always, for an ideal gas at least. I don't know if this was considered that or not, because we know Cp is equal to Cv plus R. This is equation 6 from the lab. That means if I divide by Cv, this is gamma is equal to 1 plus R over Cv. So technically, I should be able to find Cv from this equation being what? R over Cv is gamma minus 1, so it's going to be R over gamma minus 1. Okay, unless I made a mistake in here, this should be correct. So we have gamma. I mean, we have CV, so we really don't need any of the other two. So if you give me CV, all I have to do is divide R, which is 8.34, divided by this number, and I should be able to find 1.4. So technically, this also should be 1 plus 8.314 divided by 20.5. This should be also 1.4. So in other words, if I know one, I really don't need the other. Let me just check for the sake of argument in here that I'm getting the actual number. 8.314 divided by 20.5. And the answer is 1.4055 something in here. So it's actually, there is a rounding in here somewhere in there. So it's not exactly 1.4, but roughly you're going to take it to be 1.4. So that's gamma given to you already a part of the problem. So we're going to take gamma that is given in here. And we're going to take the CV also that is given. Actually, I don't trust that much to the CV, but it's fine. Okay. A, calculate the total work done in one cycle in each cylinder of this engine. So we need to find the work. We need to find this area in this path. Obviously, we found the efficiency of this engine part of the lecture. So part A. The efficiency, if you guys remember, sometimes it's written this way, is 1 minus 1 over R to the power gamma minus 1. If you don't, let me see what equation in the book is for, what the equation is. It's equation 20.6 in the book. Okay, and it's actually part of the summary also. Okay, so this is the equation that I'm using, and we proved it actually in lecture 2. So this is basically how we're using it, what we're going to be using. So we know what the efficiency of this engine is going to be then. We know that the efficiency is going to be 1 minus 1 over R. R is 10.6 times gamma minus 1. Gamma is 1.4 minus 1. So the expression, that's what I was saying in the beginning, you really need a calculator that can do these powers. Okay, so we're raising this to the power 0.4. So if I do the calculation and I'm careful with it, so what I have in here, I have 1 minus 1 over 10.6. And you have to be very, very careful with this calculator stuff, okay? Especially if you're going to do this on your own. Please make sure you take advantage of the parentheses to make sure your numbers are properly grouped, okay? You don't want to raise the whole thing to the power 0.4, and you don't want to subtract something, and you don't want to get a negative efficiency, and you don't want to get an efficiency more than 100%. So here is how you know you went wrong. If E is less than 1 or greater than, it must be greater than 0, that means you are not wrong. It doesn't mean that you're right, but you didn't do something horrible in the calculator or something, and you ended up with something nonsense. And this is true for all engines. You cannot have a negative efficiency. It doesn't mean anything. It doesn't exist, because the efficiency is always positive. Okay? It's the ratio of the absolute value. This is how it's defined, actually. E is the net work in absolute value divided by the Q hat, and the Q hat is always positive because that's energy added to the system. But just to make sure there is no ifs or buts about it, we put it also in absolute value, so that E is positive by definition. So it cannot be negative. The efficiency cannot be negative. It has to always be positive, number one. Number two, by the second law, you cannot really have an efficiency that is 100%. That's by the second law of thermodynamics. So it has to be less than 1. The first law of thermodynamics says that the maximum you can have is 100%. And actually, you cannot even have that according to the second law. So if you find an efficiency of 127% or 300% or 1,000%, that means you made mistakes somewhere big time. So that's how you catch yourself. That's one of the things that you can go immediately. So if you find yourself in one side or the other, you know that you did something wrong. You have to go back and check your work, okay? At least this way, you may be safe. So the value I'm getting in here is 0.61106, I'm sorry, which is 61.1%, okay? That is the efficiency of this engine. But I'm not asked about the efficiency. I wanted to find the work. Since I know this ratio is actually the same thing as the work that is done in this engine divided by the heat, and the heat is given to me. It's 200 joules that is added. So this is divided by 200 joules. From here, I can find what that net work is. So the net work that this engine does in each cycle is going to be 0.611 times 200. And that is, it's clearly 2 times 1 is 2, 2 times 1 is 2, 2 times 6 is 12. So it's 122 joules. I have 3 sig figs in this problem all the way through. So that answers that question. Okay, so if you can find the efficiency and you already have no one of the heats, you can find what the other one is. If QC was given to you instead, so in this case, you can express this entire expression also in terms of QC, which says that 1 minus QC over Q hot. So you can say that is the efficiency. So if you know the efficiency, you can find also what QC is. If you're given QC, you can find what Q hot is. So this is the same expression. So if QC is given, then I can find Q hot. As a matter of fact, we can find quickly QC in here. It's going to be simply equal to it's 1 minus E. So it's just the difference between minus E times 200 joules. So QC will be equal to 1 minus, I mean, absolute value, of course, it's going to be a negative number, really. So it's 1 minus 0.611 times 200, or actually it's very easy. It's 200 minus this number. Because here is how the engine is. It takes Q hot, does this work, and dumps the excess energy into so it took 200 joules. It did work of 122 joules. So the difference, which is 78 joules, is gone to the outside. So if QC is ever asked, that's how much it should be. And this is by the first law of thermodynamics. That's what I'm using in here. Conservation of energy. Okay. So that is part A. How are we doing in time? Good. So we answered part A. That's all the question about part A. I mean, I know when I'm solving these problems with you guys, and you know that now by now, I'm going way outside of the scope of the question, because I'm hoping that these further explorations will help you understand better and actually also answer more questions about these problems and things like that. So part B. Calculate the volume of the air fuel mixture at the point E. A. So we need to calculate VA. I already prepared that for you guys. If you guys remember, this is a discussion that led us to VA is equal to VC. Is equal to VC? That's wrong. Sorry, this VA is equal to VD. Glad we came back to it. And this is VA and man, this is backward. I'm sorry, guys. It's clearly from the picture, you can clearly see that VB is equal to VC and VA is equal to VD. So this is nonsense what I wrote in the beginning. So that is VC. VA, yeah, no, actually, let me delete VC. I'm sorry, why is it not deleted? Delete that further. So VA is equal to VD. So these two volumes are the same, okay? Please correct these things, especially when I'm talking. Sometimes I say something and I write something else. And sometimes when I'm thinking of something and writing something else, please correct these things on the fly. Or after you go back through them and do the calculations, please correct them. So we can use this formula to find what this volume is. I'm sorry, they want VA. What? Wait a minute. So part of it was correct in here. The other part is the one that was wrong. Sorry about the whole thing. Please make sure you follow through. So this is the point B, actually. So I had it correct to begin with, so I corrected it wrong. So this is the point B, and this is the point actually. Yeah, this is the point C. That is that volume, and R times is actually. So we had it right. And this is VD. I'm sorry. So this is VB and VC are the same, and they are equal to V. And VA and VD are the same, and they are equal to R times as much. Is this clear for the volumes? Sorry about the confusion that I may have just injected in here. Good. Come on, guys. Okay. I don't see where the chat when you guys are. Okay, very good. Very good. So I have to remove the. Okay, so let's continue then. So we have the formula for part B. So we need VA. VA is going to be equal to 1 over R minus 1 times the area times the stroke. So it's 1 over R minus 1 times the area, which is P times D over 2 squared, times the stroke. And let me write the numbers now. 10.6 minus 1 times pi times the diameter. The diameter is 82.5 divided by 2 squared times, I know about the millimeter and the meter. We're going to do that. We're going to take care of that immediately. Times the stroke, 86.4. Now, I have 10 to the negative 3 millimeters in a meter. When I cube that, because I have it squared in here and in here another one, so it's going to be 10 to the negative 9 cubic meters. And I probably will need it in cubic meters, so this is a conversion. This is another mistake that I have seen it time and again. When you are under stress in an exam environment, sometimes you don't think and you think fast and you get it wrong. You think, okay, there is 1,000 millimeters in a meter, so there's a tendency there either to multiply, which makes it worse, or just to divide by just 1,000, which is actually still wrong because you're cubing that number. Don't forget to raise it to the power 3. So if I plug in the numbers in there, and at the end we're going to have, so I have pi times open parentheses 82.5 divided by 2 the whole thing squared, okay, times 86.4 and divided by that 9.6, which is just the difference between the two numbers. So it gives me this number, which has so many, so I'm gonna write it, it's giving me 48,110. So it's 4.8 times 10 to the power 4. But don't forget I have 10 to the negative 5 and negative to the negative 9. So it's going to give me 10 to the negative 5. So the correct answer is 4.81. I need 3 sig figs times 10 to the negative 5 cubic meter. So I need that volume. So this is VA, which happened to also be V, the last point, which is D. Okay. And they want us that. So calculate calculate the volume of the air, fuel, and textile at point A. Calculate the pressure, volume, and temperature of the gas at points B, C, and D in the cycle. We're going to need the number of moles. So they want us to find PB and VB. VB, we know it already. It's just this number divided by R, the previous number divided by R. So they want us to find the volume in point B, the pressure in point B, so this volume and this pressure, PB, and they want us also to find TB, the temperature in point B. They also want us to find the pressure in point C and the volume in point C, which is going to be just the other number divided by R. Oh, I'm sorry. Hold on. What did I do in here? I have to multiply this by R. Oh man, we calculated the wrong volume. We calculated the volume in points, actually the other points. So we have to multiply this number by 10.6. Okay. You guys need to interject. I know you're doing this 4.81 times 10.6. Okay. It's 5 point actually. 5.10 times 10 to the negative 4 cubic meter. This is the volume in point A and D. So it's the other volume is basically this volume. Okay, because I did not include R in the beginning in the calculator, and I can show you that. Let me stop sharing the screen and share with you this calculator just to show you that I calculated it wrong. So if you clearly see in here, in my calculation is just divided by 9.6, but I didn't really multiply it by 9.6. So I had to multiply it at the end. I mean, I didn't multiply it by 10.6. So I had to multiply it by the end by 10.6. So this is just to show you that the numbers should really be fixed in here. So these volumes that I calculated were actually for the points. Sometimes it's hard to do things while you're explaining them, which is another point that you really have to do for this exam stuff, that you really have to be very, very focused on the calculations because it can go wrong. Since you just joined us, Jacob, you missed 38 minutes of the problem, and hopefully you're going to go back and revisit it and see a couple of mistakes that I made. One of them, it was not a mistake, I corrected it, and then I corrected my correction, which was back to the original state. And this one actually was wrong. It has all to do with this volume business, okay, which is very important in this problem. Okay, so we found the volumes in A and D. Where are they? We found the volumes in A and D, and we actually accidentally also we found the volume in point B and C, because that was this number, 4.810 to the negative 5. And this is the volume, which is 10 times, roughly 10 times more, 10.6 times more. And the other point, basically, A and D. So we have the volumes. But we need these pressures, and we need the temperatures also in TC, this point C. We also were asked about the same question about the point D. So we need this pressure PD, and we have the volume already calculated, and we need the temperature TD. So we have to calculate everything. And because we're going to be needing N, because we're going to be using N equal PV equal to nRT, so we're going to calculate N from this expression. N again is PA VA divided by RTA. We just found VA. We have PA is given. PA is 8.510 to the power 4 Pascal. And the temperature TA is 300 Kelvin, and R is just 8.314, which is a constant. So we can find the number of moles for this part. So part C, we need N. N is equal to PA VA over R TA. Okay, the pressure PA is given to be the starting pressure 8.5 times 10 to the power 4 Pascal. The reason why I'm using everything in metric system is because I'm going to use all the units in the metric system. So that's why, I mean, the volume is the size of the cylinder was given to us in millimeter, but we're converting everything to meters because we need this one. So this is the volume in point A, which is 5.1 times 10 to the negative 4 cubic meters. So everything is in SI. So this is in joule actually, divided by R, which is 8.314 joules per Kelvin per number of mole. So, and in here, the temperature is actually 300 Kelvin. So everything is going to be a number of moles at the end. So everything is going to be fine. So if we come in here and use the correct numbers in here. So what I have in here, I have 8.5, 10 to the power 4 times 10 to the negative 4, so they cancel. I really don't need to cancel to deal with this power stuff in here, so it's good. So we just need to deal with the numbers without powers. So times 5.1 divided by open parentheses 8.314 times 300. And the number of moles turns out to be 0.0174 moles. Okay, usually they don't try to do with an E at the end. They're just like a unit, basically. Okay, so this is the number of moles that we're going to be needing because we're going to be asked to find all of the points. Basically, that's what the question is. Find the VB, which is already found, PB, which we need to find, and so on and so forth. Okay, how are we going to do that? We know that A and B, this process is an adiabatic process. So this is an adiabat. So we know then PB times VB to the power gamma is equal to PA times VA to the power gamma. This is because it's an adiabatic process going from A to B, okay? So the volumes and the pressures are related to one another through this relationship. Then I can find from this expression, and this is very useful for your lab too, for your exam. So you really need to remember this one. That's because this process is an adiabatic process. If I take, for example, the Stirling engine, which is the example that probably we will not be able to get to, this relationship is not the same. We're going to use the isothermal relationships in there. So the Stirling engine is similar to the Otto engine, with the exception that instead of you have adiabatic processes, you're replacing them with a couple of isothermal processes, and you still have these two isochoric processes. So that's problem 56. Okay. So in this case, we have an adiabatic process. So that's why we're going to use this relationship. Okay. So that means PB, which we're asked to find, if I do this math in here correctly, is equal to PA times VA over VB to the power gamma. But I know this ratio. This is actually R. VA over VB, that is actually R. So this is simply PB is equal to PA times R to the power gamma. I have R, I have gamma, I have PA. So this is 10.6, that's what R is. Gamma is 1.4 times PA. PA is equal to 8.5 times 10 to the power 4 Pascal. So from here we can find we can do the algebra. So let's do 10.6 to the power 1.4 times 8.5. I'm not going to deal with the power right now because I'm going to add it later on. So it's giving me 231.65 or 232 times 10 to the power 2. Add to it 10 to the power 4. So it's going to be 2.32 times 10 to the power 6 Pascal. Obviously, the pressure has increased a lot from basically just under atmospheric pressure to something about 100 times the atmospheric pressure. And that is fine. That is actually normal for a compression of this type. So you're compressing the gas. So the pressure has to increase. You're going through an adiabat, which is so-called precipitation, which goes so fast in this case. So you're going from very low pressure in here to a very high pressure at this rate. So the PB is fine. So the fact that we found it that way. Now we know what VA is. VA, we already calculated it, if you wish, and VA is equal to, it's this number, 4.81 times 10 to the negative 5. It's basically just this number divided by R, okay? It's 4.81 times 10 to the negative 4, 10 to the negative 5, I'm sorry. It's smaller. Cubic meter. Again, this volume is a tenth of this volume, basically. This one over the other one is 10.6. That's the compression ratio. So it shrunk in size. That's what compression means, okay? And so we know what VA is, and they ask us for TA. TA, you have two options to find it. Either use the ideal gas law, which since you know PA, you know, this is not PA, this is PB. What am I doing in here? This is PB there. We're doing point B. All of this is for B. Okay. So we have PB, we have VB, and we are saying it's equal to an RTA. TB, I'm sorry. So that gives me TB then, which is simply equal to PB, VB over NR. And I have N already, and I have PB. I just calculated them. So this is going to be 2.32 times 10 to the power 6 times the volume, which is 4.81 times 10 to the negative 5. And the whole thing is divided by N. And N, if you guys remember, is 0.0174, 0.0174 times R, which is 8.314. And from here, we're going to find TB to being what? It should be a higher temperature. From the graph, it should be more than 300 Kelvin, if you guys remember. This was 300 Kelvin. So this has to be higher temperature because it's sitting higher than the other one. They are not on the same isothermal. So again, 2.32. The powers in here, I only have just to cancel this and that, and it will be just left with 1 in here, times 10 times 4.81 divided by, open parentheses, 0.0174 times 8.314, and close the parentheses. And the answer is 771 Kelvin, as expected. Okay, so this is point B. I'm going to calculate point C, but I'm going to leave that the point D for you guys because point C is important. So let's do point C for C. We already know the volume. VC is equal to VB, is equal to this volume, 4.81 times 10 to the negative 5 cubic meter. Now we need to find that pressure. That is a key for calculating the temperature. Because once we find the pressure, we're going to use the same formula. TC is equal to PC times VC over NR. So we need to find that temperature. They told us already how much heat was added in this cycle. Q hot, if you guys remember, in this case, because it's an isovolumetric process, an euchoric process, delta U is just equal to Q hot in this case because W is 0 in an isochoric process. So we have QH, which is 200 joules. That's what they gave us. This is equal to N times CV times T final, which is going to be the point C. The initial point is TB. Let me show you what that is. On this diagram, we're going from the point B to the point C and gaining heat, which is given to us 200 joules, which is NCV because we're going at a constant volume. So it's NCV times the change in temperature, TC minus TB. Since we are just found what TB is, so we should be able to find what TC is. So we have all of the information. CV was given to us actually, which we could have calculated, but that's an unnecessary thing to be given. We have N. We can find from this expression basically what TC is. So TC minus TB is going to be Q hot over NCV. So TC is going to be TB plus Q hot over NCV. Obviously, this is positive. Everything is positive in here. So TC is going to be hotter than TB. And it's clear from the picture, it must be, because you're heating it up. You're adding heat to it. It was in TB, so you're supplying heat to it with no work, with no expansion. So in this case, the temperature has to increase. And that's what it's going to be. It's going to go to TC. So it's normal to have it higher than the previous one. So the first one was 771 Kelvin. We just found it, plus, we just found how much TB was, plus Q hot, which is 200 joules, divided by the number of moles, which is 0.0174, times CV, which is 20.5. That's given to us. And everything is in SI, so I'm not worried about the units or anything like that. So it's 771 plus 200 divided by the number of moles, which is 0.0174 times 20.5, close the parentheses. And it's telling me it's 1,332 Kelvin. So this is TC is 1,332 Kelvin, okay? Which is the highest temperature in this case. So this is the highest temperature in here, in this process, okay? Okay, I'm gonna leave it to you guys to find what PD is, because we know what VD is. VD is actually the same volume as VA, and VD is going to be exactly equal to, where is the volume VA? Point A. Yeah, point A was the first one. So VA, which is, we wrote it to be VA, VD is 5.1 times 10 to the negative 4 cubic meter, okay? So that is the volume in that point. So we know what that volume is. So we can find PD using the same adiabat, because in the process, I forgot to probably mention that. Yeah, we did it for this process. So this is from B to D. I'm sorry, from B to C. So the last process that we have to worry about is the process from C back to D. And this is another adiabat. And in this case, what I can say in here is that VC to the power gamma times PC is equal to PD times VC to the power gamma. From here, we should be able to find what that PC is. That PC is going to be the ratio of, what am I saying in here? This is D. PD times VD to the power gamma is equal to PC times VC to the power gamma. This is because it's an adiabatic process. Since we're finding PD, we know what PC is. PC is actually this pressure. Did we calculate PC or not? So we found TC. We didn't find the, we have the volume, but we need PC also. Actually, that was one of the questions we were supposed to find. So we didn't do that. We need to find that pressure in that point. So you have two options now. You know PV equal to nRT, and PV equal to nRT is for the point C, you have PC times VC equals to nRTC. We just found what TC is. So we can find what PC is, which is nRTC over VC. So PC is equal to 0.0174 times R, which is 8.314, times 1,332. Divide that by that volume at that point C, which is a compressed volume, and that is a volume of 4.81 times 10 to the negative 5. So this is 4.81 times 10 to the negative 5. Okay, so this is going to be also the highest pressure in the process. Okay, it's going to be higher because we went higher. We basically increased the pressure without changing the volume. So because there is too much heat in there, added in there. So with the heat, the pressure will increase too. So it's going to be 0.0174 times 8.314 times 1,332. Divide that by open parentheses 4.81, and I'm going to leave the power for later on, okay? So it's going to be 40.06 times 10 to the power 5, okay? So I'm going to write it in scientific notation as being PC equals to 4.06, not 0.00, 0.01, I should say, times 10 to the power 6 Pascal. If you look at the pressures, if you keep tab of pressures, this should be the highest pressure. So P, did we find PB? PB was 2.3, and this is twice as much. okay, to increase to about 4 times. 4 times 10 to the power 6. The other pressure was 2.32. That's in point B, so it's a little less. And in point A should be, it was actually 10 to the power 4. That's what we started from, 8.5 times 10 to the power 4. So the pressure steadily went up from 8.5, 10 to the power 4 to 2 point something, 2.32 times 10 to the power 6. And now it has increased, doubled basically in value to 4 times 10 to the power 6. Obviously, PD should be less. It should be more than the first pressure, but less than both of them, actually, according to this diagram. So let's find what that pressure is from this calculation. So we need to find what PD is in terms of PC. PD is going to be PC from this expression times, and that's why we need actually PC too for this calculation, the ratio of the volume of VC over VD. And this ratio is actually, to the power gamma, is 1 over R, because VD over VC is actually R. So again, this is PC times 1 over R to the power gamma. So PD from this calculation, PD is going to be equal to PC, which we just found it to be 4.01 times 10 to the power 6 times 1 over R to the power gamma, and R is 10.6 to the power 1.4. So let's plug in the numbers. 4.01 divided by 10.6 to the power 1.4. So it dropped by a factor of 10 to the power 1.47 times 10 to the power 5 Pascal. It's less than the other two pressures because both of them, they have 10 to the power 6 Pascals in it. And it's more than the first pressure because the first pressure has 10 to the power 4 in it. So it's clearly where it needs to be in terms of this pressure. So we found PD. And then you can use PV equal to nRT in this case. P in this point is PD times VD is equal to nRTD. You can use this expression. Now you have R, you have N, you have the volume in D, which is the same volume in A, and you have PD, which you just found. You can find what TD is. And the TD, again, is not going to be, it's going to be an intermediate value for the temperature, okay? So I'm gonna leave this to you guys. Finish. Okay. The reason why we need this, we need TA as 300 Kelvin, that's given to us, and we need the hottest temperature in this problem, which turned out to be TC, which is 1,330 Kelvin. If we're going to compare it to a Carnot engine, in this case, its efficiency will be, it must be more than 61%. We found the efficiency of this engine to be 61%. So this efficiency of Carnot, had it really operated as a Carnot, and it's not, because it's an auto engine, how much efficiency is going to have? So it's going to be 1 minus 300 Kelvin over the hottest temperature, the lowest temperature over the hottest temperature. So this number, if you do the math, it's 1 minus 300 Kelvin divided by 1,332 Kelvin, and the efficiency is 77.4% or 77.5%. Obviously, our engine in this case for the VW Passat, the problem that we have before us, is 61.1%. So it's clearly less than Carnot engine. Had it operated as a Carnot engine, it would have been better under the other circumstances. Okay, but it's not. So it's less efficient than that. Okay, so that is basically how this thing is. So this is in compliance. E for this VW Passat is less than E Carnot. Nobody can beat it. Okay, because it's operating between the same two temperature, hottest and lowest. Okay. I don't know if this question is asked or not. Compare the efficiency. Oh yeah, that's question D. Compare the efficiency of this engine with the efficiency of Carnot cycle operating between the same maximum and minimum temperatures. So this is a comparison. So this is actually question, I lost track of the numbers now. Question D is to compare, and this is typical. So when you have a problem involving engines, they always ask you at the end, how does this compare with Carnot engine? That question, you always have to find it less than, it cannot be better than Carnot engine. So in this case, Carnot engine, if it was operating between these two temperatures, will have an efficiency of 77%. However, this engine's efficiency is 61%. So nothing can beat Carnot engine, including this, the one that is in the VW Passat. Okay. I know it's extensive, and I know we went through a lot of calculations, and we didn't even answer a part of it. But I'm hoping that you guys learned something from this kind of problems. And I want you to finish it and actually do it and understand all of these things, okay? At least next time when you see somebody working on an engine and you look at the cylinder, you know what's going on inside in that, okay? Or if you want to do it as a hobby, which is a great hobby, okay? So the other problem that I promise we have to do no matter what today is problem 52. So let's tackle that problem 52, okay? And I mentioned that actually in lecture also a little bit briefly. So the other problem is problem 52. This is not as involved in terms of the math, but the idea is actually a very interesting one. So it says to heat up 1 cup of water, it's basically the volume of this water is equal to 250 cubic centimeters, okay? To make coffee, you place the electric heating element in the cup. So you have a cup, okay? And you bring, usually it's a heating element, which is a resistor that has this shape. And then you put it inside the cup, okay? And you connect it inside the cup. As the water temperature increases from 20 degrees to 78 degrees, so the water temperature, T initial, is 20 degrees Celsius. It is a must to convert it in this case, if you're going to be calculating with entropy into Kelvin. So you have to add 273. It's 273 plus 20, which is 293 Kelvin. So this is the lowest temperature. That, I mean, you want to heat it up. So you want to bring it to a higher temperature. So the T final, which is T2 in this case, they wanted to come up to 78 degrees. And that too, we have to add to it 273. 8 plus 3 is what? This calculation probably may require a little bit higher precision because the actual conversion is 273.15, okay? But let's see here if we can get away without doing that. 8 plus 3 is 11. 8 plus 7 is 15. So this is, according to the numbers, 351 Kelvin. Okay, so this is the final temperature that we need to achieve. Calculate the change in entropy of the water. That's why we needed this. It's for the entropy of the water. Remember from lecture, and you can easily show it, that each time the amount of heat basically is added to the water, which is equal to MC dt, then in this case, the entropy ds is going to change by an amount dq over t, which is given by MC dt over t. When we sum it up from T1 to T2, that is going to be the change in entropy for the water. So the change in entropy is from T1 to T2. And in this case, I'm going to be this whole thing, dq over t. So it's going to be MC times the integral from T1 to T2 of dt over t. And that is the natural log. Okay. It's MC ln of T2 over T1. Okay. And that's why we needed to convert this one. If I'm going to do this ratio, I have to be careful in here. It has to be in Kelvin. It cannot be in degrees Celsius or any other unit. Okay. So the change in entropy in here for the water, you need to know that the specific heat for water is 4,190 joules per kilogram per Kelvin. So you need the mass of the water. Now the density of the water also is 1 gram per cubic centimeter. And they told us the volume of this water is 250 cubic centimeters. So the mass of this water is 250 grams or 0.25 kilograms. Okay, so we need M and we need C, both of them. So what I have in this case is 0.25 times 4,190 times ln of 351 divided by 293. So this is why we needed to do that conversion. So in this case, it's just a matter of doing the algebra now. And it has to be a positive number because the water temperature went up, so its entropy must have gone up, okay? So 0.25 times 4,190 times the natural log of open parentheses 351 divided by 293 and close the parentheses. And the answer is telling me it's 189.2. Okay, the units for it are the same units as joule per Kelvin, because remember, the definition is dq over T, and dq is actually in joules, and this one is Kelvin. So the units for the entropy is joule Kelvin per Kelvin. Okay, so that's how much the entropy of the water went up. Okay. B, the system, no, B, the heating element. This is why I wanted this example. It's very important, and I made a big deal of it because in the past, students, when they do calculations like this one that involve phase, not necessarily phase transformation, even in this case, they may be tempted to say, oh, maybe the element in here is not heating up. Seems like it's, I mean, there's no heat in this case because its temperature is not changing, because I tell you specifically in the problem, the water temperature, the temperature of the heating elements remains constant. So it's an isothermal process for the heating element. But it doesn't mean that there is no heat exchange. As a matter of fact, it's losing heat to the water, and that's why the water gets hotter. So it's not because of the fact that for the heating element it's an isothermal at fixed T doesn't mean Q is 0. No, this is not correct. Okay, as a matter of fact, we can find how much heat exactly it has. The heat that it lost is the same heat that went to heat the water. And I know that the heat that warmed the water is Q is equal to MC times delta T. For this case, it doesn't matter to the conversion. But in this case, I know how much heat is. It's 0.25 times 4,190 joules times T final minus T initial, or 78 minus 20, or 351, if you care to write it this way, minus 293. Okay? So that is the amount of heat that this heating element has lost to warm the water, because the water must have gained heat. Where did it get from? It got it from the heating element. That's the purpose of it, actually. So it's going to be 0.25 times 4,190 times open parentheses 351 minus 293. And that is going to be 60,000. So this is the heat, the one that went to the water. For the heating element, it has lost it actually, by conservation of energy. So it's going to be minus 60,755 joules. It did that at constant temperature, though. So in this case, the change in entropy for the heating element is going to be just Q for it, for the element, divided by its fixed temperature. Okay? Its temperature stays the same at 78 degrees. I'm sorry, 120 degrees. T fixed. The water is the one that needs to go. So the T of the fixed, it operates at 120 degrees Celsius, okay? Which we need to also convert by adding to it 273. So it's going to be what? 393 Kelvin. Okay, 393 Kelvin that needs to be basically included in here. So this is how much it is: minus 60,755 divided by 393, and that is the entropy that the actual heating element must have lost in the process, okay, because it lost heat. So its entropy must go down. So in this case, it's minus 60,755 divided by 393, and it's negative 155 joules per Kelvin. This is how much it lost. And it has the proper units because this is the units in joules and this is the units in Kelvin. So we're in good shape, okay? So that's how much entropy it has lost. And then part C, the system, the entropy for the system of water and heating element. So it tells you in here, make some assumptions. One of them is that heat that flows into the ignore the heat that flows into the ceramics and coffee cup itself, because there is some heat that is going to go to the cup itself, to this container. Okay, so we're going to ignore that, and we're going to focus only on the system, basically water plus heating element. So in this case, the delta S for that is going to be that of the water, added to it that of the heating element, and this must be overall positive, okay? And I will say why. So it's 189, was it 189? Yes, 189, positive 189, minus 155, and this is going to be equal to, I rounded that number, by the way. It's not 155, 154.6 to be more. So 189 minus 155, it's positive 34 joules per Kelvin. And this is in compliance with the second law of thermodynamics. Second law of thermodynamics, it says that in any thermal process, the entropy of the universe must increase. So yes, you're worried in here, didn't it decrease for the case of the heating element? And it did, because it lost heat. But it also increased for the water because it gained heat. But overall, the universe itself, by this process, by the fact that you wanted to warm your coffee, saw its entropy increase. Everything we do, whether it's biological system, a non-biological system, like for example, industrial process or any other process, will result in the increase in the entropy of the universe, So this is no exception to that. So that is a typical example in this case. Does this make sense to you guys? This example? Yes? There's a problem, actually. It's not an example. Okay, so we're doing it from the book. Okay. I'm going to discuss how much time we have left. We have left about 10 minutes, and we have quite a few problems to discuss. Let me discuss how these problems go. Okay. Problem 53. I hope that you guys are doing this. You're not just watching me do these things, because that's part of the stuff that we do in problem sessions. If we're doing this on campus, I don't do anything on the whiteboard or I don't write stuff. You guys do. So I always have you guys go on rotation, and each time one of you guys solves the problem and we do another problem and so on and so forth. But that's basically the ideal world. So right now, I'm assuming that you guys are actually doing these things, not watching me do them. And yes, as I'm explaining them, sometimes I type things that are not correct. So I really want you to be at your own utmost focus when you're doing this problem, especially when it comes to exams, because you have to keep up with so many tiny things, okay? And they're important. Every step, if you make a mistake in one step, you're going to basically suffer the consequences for the next step and so on and so forth. So you really have to focus on those things, which brings me to an important point, and I know I made a big fuss over it in the past, and that is to show your work, to give yourself a chance so that I can catch where the mistake is, so that I can give you credit for the next steps. Because if you make a mistake in here, and you end up with some nonsense result. For example, you end up with an efficiency that is more than 100%, or you end up with a temperature that is, for example, too big, and all of a sudden your efficiency now is probably better for that process than a Carnot engine, which you know is nonsense. Then at least second trace back, and you lose the points where you made the mistake, but you don't suffer the consequences because you did all of the steps later on is correct. So you need to show me your work. So when I'm grading this, because I'm going to override what Canvas says and give you credit for when you need to have credit for it. Okay. So I'm hoping that you guys, this is an important thing that you're doing, and you're actually doing that for you, for your sake. Problem 53. Let me discuss problem 53, and hopefully you have the book open or you have your notes open also. So it says, in your summer job with a company, it says venture capital firm, you are given funding requests from your inventors of heat engines. So, and the inventors claim the following. So you get collect data, and you're making decisions into which engine you would want to go with for your company, okay? And they tell you, okay, you ask specifically, give me the TC, the lower temperature, give me the T hot that you would want to operate with, and give me how much efficiency do you think you have computed based on your model, okay? And the processes involved. They tell you do this process, that process, another one, this process. This is how much efficiency, this is how much efficiency, and this is how much efficiency, okay? Obviously, you have other factors to consider other than efficiency, but that's one of the things that they give you. For some reason, the efficiency is expressed in this problem in percentages, so they are all decimal points, okay? So the first engine has a TC 47, T hot 177, and a temperature, an efficiency of 21%. TB, again, you do the same thing. The second process, the prototype B, prototype C, and prototype D. So you have them all, okay? Prototype C, interestingly, works between a negative 33 degrees Celsius all the way to 247 degrees Celsius, okay? So those are the temperature in degrees Celsius that were given to you. Based on the values that they gave you for TC and T hot, find the maximum possible efficiency. So what do you do in this case? You take TC and T hot that they gave you, convert them first of all to Kelvin. You have to do that. And you do basically 1 minus TC over T hot. That's going to give you the maximum efficiency that you should have from these engines. So if you're going to compare them, you cannot look at their temperatures or their efficiencies. You really have to compare them based on something else. So in this case, what they are telling you to do is take those temperatures and see how much, if they operated as Carnot engines, how much efficiency they have. And the formula for a Carnot engine is 1 minus TC over T hot. TC and T hot expressed in Kelvin, though, not in any other temperature. So you must convert the temperatures they gave you into Kelvin, including that negative 33 for prototype number C. It's going to be a positive number because negative 33 plus 273, that's going to be a positive 240 or something like that, okay? Positive 240 Kelvin. So all of them are going to be positive. So it's going to be 1 minus 240 divided by 273 plus 247. You can do the math. The point being in here, you're going to find the efficiencies of all of this engine as they compare to Carnot engine, okay? Are any of these claims impossible? Let's say, for example, one of them claimed to have an efficiency more than their equivalent Carnot engine. Of course, you have to reject that immediately because there is something wrong in their calculation. So you're going to look at the efficiency of each one of the claimed efficiencies and compare it to a Carnot engine and see, is it less? If it is less, then maybe they did right. If it is more, then you have to reject it from the get-go and tell them, hey, this is not acceptable. You have had somehow an engine that is more efficient than Carnot engine, and I know by the second law this is impossible. Okay, so you're going to reject that prototype based on that. Okay, and then for all prototypes with the efficiency that is possible, rank the prototypes in decreasing order of the ratio of claimed efficiency to maximum possible efficiency. Here is how you're going to make your decision. Let's say, for example, you rejected the 1 or the 2 or the whatever number that you ended up with that are wrong. Get them out, okay? Now you'll be left with a handful that are actually feasible in a sense that their efficiency is less than Carnot engine. So what you do in this case, you take the ratio of the Carnot efficiency divided by their efficiency. And the closer their efficiency to a Carnot engine, the better they are. The more money you get for your buck. So it's not the efficiency, how efficient an engine is. It's not you rank it from highest to lowest. No, that's not. You rank it from how good it is versus how it could be. And that is basically how you're ranking this. So how efficient it is versus how much it could potentially be. And that is how close they are. That is basically how you're going to make your money. That is how your engine is actually good. That is why the claim is in problem 56 that Stirling engine will come closer to a Carnot engine than any of the other engines if you compare them apples to apple. In the problem that we just did, problem 47, the efficiency was 61% and Carnot engine was 77%. So I'm comparing it, I compare 77 divided by 61. So it's going to be, how far is it? It's not the difference though. It's the percentage difference, okay? So it's going to be 61 over 77 or the other way around. 61 over 77.5, that is. So it's about 79%. So it's about 80%, or slightly less than 80% efficient had it operated as a Carnot engine. So that's how I'm going to compare that VW Passat engine to a Carnot engine, okay? So Carnot engine is still 20% more better than that one, okay? So that is problem 53. We still have about 4 minutes to discuss. Okay. I already mentioned problem 34 and problem 39. Actually, I did not mention 39, but those two problems, they're exactly what we did in the lab. And add to them problem 37 too. They are actually all three of the overall engines that you have in the lab. So you need to review the lab again and do the calculations and then, and if you have difficulty with them, please let me know. Let me talk now about, and that is actually example also 49. So 34, 37, 39, and 49 are similar to the lab, which makes a lot of weight on the lab in terms of your exam preparation. So you need to do the lab, all of the eight cycles, okay? Eight processes, 8 cycles, I'm sorry, 8 engines. So do those. And if you do them and understand them, you shouldn't have difficulty with at least this part of the exam, okay? Problem 42, though, is slightly different. Problem 42 now, process A to B, if you're looking at it, is an isobaric process. Process B to C, that's an isobaric process. It's process C to A that is none of the above. It's not an isothermal process. It's not an adiabatic process. It's not an isochoric process, and it's not an isobaric process. It's none of the things that we did in class. So how we're going to find the difficulty in there is finding the heat. Finding the work is easy. Finding the work is just the area end of the graph, and that is easy because it's going to be just a straight line. So it's going to form basically a triangle, and the area of the triangle is 1/2 the base times the height. Okay, so we know the area. Add to it the rectangle below it, and that's it. That's the whole area. So that's the work. The question is the heat. Here is the thing. If I can find the overall change in energy, which is 0, and if I can find the overall work, which is fine, which I can find by the area inside the triangle itself. So there is a triangle ABC. If I can find that area, that is the work. That is the net work, okay? And since I can find the heat involved with AB, because that's an isobaric process, so that's easy to do. And if I can find the work between B and C, that is an isochoric process. So the first one is NCP delta T, or NCP times TB minus TA. And the other one is going to be NCV times TC minus TB. So now I have the heat for the other two processes. What is missing is the last heat. So I use a conservation of energy, saying that since the overall change in the energy is 0, that must be equal to the net work, which I can calculate from the area, plus the net heat. So the work in this case is equal to the net heat. Since I have 2 pieces of the heat, I'm missing 1. So I have 2 pieces, they add up to the net work. So in this case, I can find the last one. So that is the trick for that problem. If you think about problem 42 and you have difficulty with it, please let me know. And I think what I will do is probably put the solution on Canvas in there so that you guys see the last. That is the trick for that problem. Everything else is straightforward, just like the other problems. Okay. Okay. Problem 22 is a fun problem also. Problem 22 deals with the entropy when you heat the bathtub, and it's similar to this problem that we just did, problem 52. Okay. So those are the problems I wanted to discuss with you guys. Please take your preparation seriously. If you have difficulty, please reach out. And like I said, I can answer. If it's a simple question, I can reply to you. But if it's something that I think it's probably worth sharing with everybody else, I will share it with everybody else. And we can go on a meeting and we can sit down and work out whatever questions you have. And if it benefits everybody else, we're going to basically record it for everybody else. Does this make sense to you guys? Okay, very good. Listen, I'm going to stop recording and the session is going to be over. So with the exception of one of you guys, you can guys leave and I'll see you guys after the spring break. How is that? Okay, there is another item that is very important. You're going to receive a communication from me about the Guardian app that you have to have in your phone and how to basically go online and fill out the requirement to go on campus. I really don't know if it's required for you guys or not, but just to make sure that you're safe in terms of when you come to the campus to visit and all of that thing, okay? So let me stop recording. And please watch out for Canvas communications regarding the exam, which is immediately after spring break. Thank you. Let me stop recording.